Polarized Light Microscopy in Archaeology. And this is Lecture 6, the real Lecture 6 this time, rocks. So rocks are very important. In the petrology, we may study rocks of various sorts, and we may, of course, find rocks in pottery. So rocks are comprised of minerals. So if you can identify the minerals, you can identify the rock. Really quite simple. There are three main types of rock: igneous, metamorphic, and sedimentary. Igneous rocks started off as being molten. They were either deep below the surface or came up to a certain extent. So it involves magma or lava that came all the way to the surface and then cooled. And so you have distinctions amongst igneous rocks based on chemistry and the cooling environment. So you can see that something that cooled here will be different from something that cooled down here or even down here. So here is a section through the lithosphere, the crust of the Earth, showing the various relationships between plates in the plate tectonic sphere. If you don't know anything about plate tectonics, you should have gone to the prerequisite course of this course. But essentially it has a number of margins. You have a spreading ridge or a creative margin or a divergent margin coming apart because of an upwelling of magma which pushes the plates apart. Here what it's doing is doing exactly the same thing, only it's creating a rift valley, just as you can see in East Africa, for example. And so these plumes will push apart the crust, creating more oceanic crust. You also have subduction zones, or destructive margins, or convergent margins, where you get one plate going underneath another one. This one's going this way, this one's going that way. Same thing's happening here. This one's going underneath more oceanic crust. See, this is oceanic crust. This is continental crust, and here the oceanic crust is going underneath the continental crust. This creates melting of the crust as it goes underneath, and takes down a lot of the material which was on the surface. And so that will create volcanism up here. These volcanoes here. Like that. You also have hot spots, which are actually probably very closely related to these, as you can see. But basically, it is thought that a single hot spot may make a shield volcano, or a line of shield volcanoes as a hot spot stays in place, but the plate moves over it, such as Hawaii. But if you get more than one hot spot, then they may crack in between them to start something like this, which you can see in the Red Sea, for instance. So, the rocks we get around here are called felsic or acidic rocks. We often get intermediate rocks and volcanoes in this position. And we get mafic or basic rocks erupting along mid-ocean ridges, along rift valleys like this, or mid-ocean ridges or shield volcanoes like this. The oceanic crust, in fact, is entirely made of mafic or basic, well, not entirely, but most of the top bit here is made of mafic or basic igneous rock. And you also have ultramafic igneous rock, which is basically bits of the below the crust, which can eventually be pushed up onto the surface. somewhere like this. So, igneous rocks. You may have volcanic rocks, often called extrusive, and plutonic rocks, often called intrusive igneous rocks. There's an intrusion of igneous rock. And so these will cool much slower underground than they will be if they come to the surface, or even if they're in a dike or a sill or something like that. And so this is the other form of distinction, that you have the chemistry, but you also have where it cools will affect the texture of the rock. So the volcanic rock is named after the god Vulcan, and who lived in a volcano, and Pluto is named after the god Pluto, who lived underground. So, like that. Oh, here you go. And so, that distinction, for instance, this is chemically the same rock. This is called Gabbro, this is called Basalt. This is very fine-grained, and this is not. And so, because it's taken longer to cool, it could grow bigger crystals. And so that's the basic difference. Plutonic, bigger crystals, volcanic, smaller crystals, and in some cases no crystals at all because it cools so rapidly. So this is a very fun diagram which I made based on other people's, and it shows you all sorts of fun things. For instance, the types of igneous rock: felsic, intermediate, mafic, and ultramafic, and how much silica is within it. So as you can see down this end, it's like mostly silica, and this isn't all quartz. It will include a lot of feldspars as well, which are all silicates. And even these other ferromagnesian minerals will have silica in them, but of course this is mostly silica, and so the more you get this way, the more higher proportion of actual silica you get in the rocks. And so you have intrusive versions and extrusive versions, or plutonic and volcanic. And so granite is the equivalent of rhyolite, diorite is the equivalent of andesite, gabbro and basalt, as I showed you, and peridotite and komatiite, which may be terms you have never heard before in your life, which shows you how very rare igneous rocks are compared to everything else, because they don't really belong on the surface, they belong deep below the surface. So as the silica increases this way, in this direction, we get increasing magnesium, iron, and calcium. And so you'll see that in these ferromagnesian minerals. Olivine, pyroxene, and amphibole are all the ferromagnesian minerals, the dark minerals. And so that means as these increase in proportion, see amphibole, pyroxene, and olivine, as these increase in proportion, the rocks get darker, and so you'll have very pale-colored granitic rocks and very dark ultramafic rocks. So if we go through these, we start with the felsic group, the granitic group, the rhyolitic group, depending on whether it's intrusive or extrusive, and you can see, and of course you know these minerals now, potassium feldspars, or K-spars as we often call them, like microcline and orthoclase. There's a lot of those in these rocks. And there's quartz, which you also know, and plagioclase. And if you remember, this has got a series going from calcium-rich end members to sodium-rich end members. And it tends to be the sodium-rich end members we get in the granitic rocks. And you'll get mica, and you'll get some amphibole. So, potassium feldspar, often pink, and quartz, often grey or white. And the intermediate group, mostly plagioclase. You see, some quartz, bit of potassium feldspar, but mostly plagioclase, and like some mica and amphibole. So plagioclase tends to be grey. Nephew balls will tend to be dark green. The mafic, gabbroic, basaltic rocks will have a lot of plagioclase again, and a lot of pyroxenes. The pyroxenes come in a big way now. Very important ferromagnesian minerals, and also very colourful and cross-polarized light, if you remember. And then we have the ultramafic, again with pyroxenes, and also with olivine. Lots of olivine. We don't see this very often, but what we will tend to see quite often in certain parts of the world is serpentine, which is altered olivine. And so that's something we do see, even though we don't actually see these very nice green shiny minerals. So this is probably giving you a headache if you've never seen this before. This is a ternary diagram, which geologists use quite a lot, and they like them. And basically, the closer you are to each corner, the more of whatever that is in there. The Q here is quartz. The P is plagioclase. And the A is alkali feldspars, or K-spars, or potassic feldspars. Okay? So granite is sort of in the middle, with, you know, quite a lot of quartz, quite a lot of alkali feldspars, and some plagioclase. Tends to be, right here, would be equal amounts of each. Right in the middle, we see. It can come over here and become granite diorite, tonalite. Granite is a very common mineral. Down here we have the gabbros and diorites. And you have monzonite down here and syenite. All these are important rocks. And you'll be able to tell which they are by what is in them. So if it has hardly any quartz and equal amounts of alkali, feldspar and plagioclase, it's going to be a monzonite. Just has to be. Can't avoid being anything else. So, of course, we see these in thin section, and sometimes you can look at the assemblage of minerals. For instance, this is microcline in a petrofabric called the Granitic Petrofabric from Belize. And so it is possible, you will not find lumps of granite in a pottery thin section, but you will find the minerals. And if they look like they're about the same size, worn down to about the same amount, you might hypothesize that they originally belonged together. And so if it turns out that it's equal amounts of potassic feldspar and quartz and plagioclase, you probably have a granitic rock. And the same thing is true. This is exactly the same thing. Now, these are volcanic rocks. And so rhyolite is here where granite was. So here on this convergent destructive boundary, this is the continent versus an oceanic boundary, you can see the melting of the crust here is creating magma, which will come up as a felsic volcanic, or if it doesn't reach the surface, it will cool and become granite. So here's a nice granite thin section, plain polarized light and cross polarized light. You've seen this before. Here are some nice amphiboles, green pleochroism. Here you can see the two cleavages. Here's some biotite. See the sparkly extinction, typical of biotite. And also in here you can see there are feldspars and quartz. Kind of difficult to determine the differences between them at the moment, but if this was actually under a microscope, you'd be able to look at it closely to see this, for instance, looks like it has cleavages. I can't see any twinning, so it's probably orthoclase. This looks like it has fluid inclusions, possibly, and so this must be quartz. And so you'd be able to work out what kind of rock that is by seeing how much of each mineral is in it. Quartz, orthoclase, plagioclase, on hornblende. Hornblende is the complex hydroferromagnesium silicate. Muscovite is the iron-free mica, and biotite is the iron mica. I can't actually see offhand any muscovite in here, but it occurs quite often in granitic rocks. Here's a nice granite. This is the Aswan granite, very distinctive, very big pink crystals of orthoclase. This is this very big head at the British Museum, and this is a close-up of it. So this is Egypt, as I have told people before, mostly in other courses about the archaeology of stuff. Egypt's very interesting, and one of the interesting things it has is very nice stone, very strongly contrasting with Mesopotamia, which just really has mud. Not a lot of stone there at all. They have to go somewhere else to get the stone. Whereas here they have, here in these red bits, this is all a Precambrian basement with lots of all sorts of very ancient, very hard rocks that are very useful for building things out of. It comes down here to this, right? Here's Aswan. You can see there's a little bit of the Precambrian basement here. But it also has sandstones, Nubian sandstone, and it has limestones. And so these nice, flat, well-preserved limestones and sandstones are also very useful, because the limestone is what you build your pyramids with, you see. So very useful having all these stones just sitting around the place waiting to be used. There's a Precambrian basement, as I said, sandstones, limestones. What's your uncle? Oh, and there's Aswan. I told you that's what Aswan was. So Aswan granite, once you get your eye in for these large pink crystals of orthoclase, you will start seeing it everywhere. For instance, this is at Palmyra Tadmor in Syria. I think this was blown up, unfortunately, but you know, it had already fallen over once. So this is Roman, or Roman period at least, and the Romans really liked to show how they controlled everything by moving everything around. And so you wouldn't just use any old granite, and I can assure you there is granite in Italy and in parts of Syria. Instead of getting local granite, they'd much rather ship it from way up the Nile just to show they can. And so here, this is the Forum in Rome, again with Aswan granite. So the stone of Egypt, the Igneous Rocks of Egypt, are subject of petrographic study, which enables people to identify production centers, mines, and where they were worked and everything. So it's quite an interesting area of study if you want to get into that. So here we have mica. This is a bee petrofabric. So this is a granitic, mostly source. It's got some feldspars and some quartz, a nice piece of biotite. You've seen this before. I'd like to show this to you. Ooh. And this is also a granitic rock. This is a perthite. Remember me telling you about this intergrowth of plagioclase and potassic feldspar, although this is probably an anti-perthite. So Felsic Volcanics include rhyolite and pumice and obsidian, volcanic glass. Cools so quickly it can't even crystallize at all. So obsidian, of course, is a very useful archaeological material, thing that people do thin section, mostly to look at the weathering to see how old it is. We do get it in pottery. This is, you can see this is lump here, probably some sort of tooth that came out of a volcano and was floating around and landed somewhere. And you can see in plain polarized light it looks like this, and in cross polarized light it's isotropic because it's glass and it's vesicular. It's got bubbles in it, bubbly glass, and also within it there are little crystals, because crystals were developing in the glass, in the molten rock before it was shot out and rapidly cooled. So we get a lot of this. For instance, in the Tigris-Euphrates basin, we get a lot of volcanic glass. Here's the famous Maya ash-tempered pottery. You can see this. These are all fragments of volcanic glass, which are thought to be the remains of ash fall from volcanoes. And you'll be finding more about that in next term. So this is a nice pot. This is actually at the ROM, and this was a study I did on pottery made in Iran. And at an early stage of this project, I had sampled all the pottery that was of this period, 15th and early 16th century in this case, and had identified some fabrics, some petrofabrics, a couple of which I could attribute to somewhere. And then there was this one. This fabric I could not identify its origin. But this should be stone paste. All of the pottery was made of stone paste. Now, if you remember, stone paste is mostly made of quartz. And this is not mostly made of quartz. But I know it is a stone paste because it's mostly got big angular things in it, which are quite often quartz. And more importantly, they put glass in it. So it clearly has the three components of stone paste. This is all anthropogenic glass which has been added, and the elements within it have come out of the glass and fused with the matrix around it. So this should be a stone paste. But what we have in here, this is a large piece of a felsic volcanic rock. And in fact, a lot of the inclusions in here is really quite dominated by this felsic volcanic. It's quite difficult to see in a photograph, but it's got very, very fine crystals growing in it, and it's clearly a felsic volcanic of some sort. So this had me thinking, this would suggest that these potters had gone to somewhere where there was no quartz. And you could imagine standing on the location of this production center, and it must be that you were in a valley surrounded by hills that were entirely volcanic, covered with volcanic rocks and that sort of thing. All the local geology uphill from there was volcanic, felsic volcanic. And I looked around. Oh, that's it, yes. I looked around and found the city of Tabriz. So most of these were from Iran, and so looking vaguely around this area, and this is a valley down here. Here is Lake Urmia, which is within the greater valley itself. And up the hills here, this is either granitic rock or it's a felsic volcanic here as well on this side. And so you can see how Tabriz is completely surrounded by felsic volcanic rocks. Practically unique situation, and so that led me to hypothesize that I thought this pottery came from Tabriz. As a result of this hypothesis, I acquired kiln evidence and tiles and other things that don't travel around so much from Tabriz, and was able to characterize this fabric as coming from Tabriz based on finding so much volcanic rock in it that there was no quartz. Oh, yes, right there. So, here we have, so, in the granitic rocks, over here we have the intermediate tonalites, granodiorites, gabbro-diorites, things like this. And this is one of those. In Egypt, there is this type of rock that is often called in the literature black granite. And there's no such thing as black granite. There's only white or possibly pink granite, not black granite. Black would suggest it's got minerals in it which would not make it granite. So it must be something else. And so here at the British Museum, where they tend to like thin section things and see what they're made of, they've decided this is granodiorite. So that's that rock down in the bottom right hand corner, more or less. So here we have again that section through the earth. So here we have the lithosphere. So this is where we get a lot of this basic volcanic rocks. Here's a gabbro and basalt. Dolerite is a very common rock that forms dikes, which are like veins through the rock, which cool more rapidly than basalt, but less rapidly as gabbro. So this will have plagioclase, clinopyroxenes, and olivine. This is olivine. Some amount of olivine, not a lot. This is in fact this probably was olivine. It's starting to turn into serpentine. But you can see that this is a basaltic rock. Had a lot of olivine in it until it was altered. Magnetite and plagioclase. Here's another one. This is actually a piece of pottery. You see there's still bits of pottery on the edge here. But this is a very nice piece of basalt with olivine in it. And here you can see another piece of basalt in a piece of pottery. So the volcanic rocks will be what you will find in pottery, although you could hypothesize that what you see is, say, a granitic rock based on the minerals you find. This, for instance, is a fabric in the Yemen. The first pottery I thin sectioned was actually from the Yemen, and I did this study back in the mid-80s now, first published in 1988. And you can see one of the fabrics had things like plagioclase and pyroxenes. There's a little bit of pyroxene. Here's a big piece of pyroxene. So that would suggest that it's getting a lot of basaltic gabbroic type material, whereas the other one had granophyres in it and biotite and stuff like that, which would suggest it's getting more granitic rocks. So this, you can see that creates a major distinction based on what was the available geology upstream from these sites. So sedimentary rocks. So sedimentary rocks are basically things that form on the Earth's surface. These are the depositional environments of sedimentary rocks. Most of this is what we would call detrital, which is bits being weathered off of other rocks and coming down. Gravity might bring it down. Water, glaciers will bring it down. It'll be deposited down on plains. And so you have rivers depositing riverine, fluvial, deltaic deposits. And the water will come out into the sea. And you'll have major flood events, say in the spring. And this will create pulses of deposition of sediment. So you can see these are different pulses, different seasons of deposition in the abyss beyond the continental margin and beyond the continental slope. So up here, you'll get things where it's not carried quite so deep. Down here, you get things like clays and things being deposited down here. Also, overbank deposit around here might be clay. But you also get a lot of sand. And things that like to pull sand together, things like beaches. So beaches will have a certain regime to them, depositional regime. And you will not get things the size of silt or clay on a beach. You'll only get sand or possibly cobbles on a beach. And so beach aeolian deposits are similar in that regard. And so you'd only in that case get sands from sand dunes and things like that. You can also have lakes and evaporites, which we should get to later on. Mechanical detrital clastic. These are three words for the same thing. Often happens in life. Mechanical, it's been broken down. Detrital, it's detritus. A clast, which means it's a broken thing. And you have chemical sedimentary rocks. That's the two main types, mechanical and chemical. So chemical sedimentary rocks will include evaporites developing here, and limestones possibly being deposited down in, like on the shelf certainly, and in the abyss. Biogenic will also be related to chemical. If it's a lot of these deposits down here will be from organisms dying, so they're biogenic. And precipitate. And so this will be because these elements precipitate out of the seawater and are deposited on the bottom of the sea. So, the mechanical detrital-clastic group, we are divided mostly, but not entirely, by how big they are, which is governed by depositional regime. So you have big things, conglomerates, grits, gravels, rudites, and breccias. You have sandstones, or arenites. You have siltstones. You have shale argillite lutites. And you have wacky or grey wacky. So this is all basically on grain size. And the chemical biogenic precipitate group will include things like limestones, chert, and phosphatoids. All very important groups. And this is two different parts of the world because it's basically showing that you get a lot more mechanical where you have land for the detritus to be detriting from and depositing in the nearby ocean. A lot of these biogenic chemical precipitate rocks will often happen in oceans, deep oceans, or there's basically oceans far away from where the land is, because the detritus will be over here, but way out here, all you will get will be things like limestones developing in cherts and phosphatoids from all the animals dying. So, don't memorize this, but you can see this is the International Grain Size Scale, and these are big things. So these are like cobbles, I guess. These look like cobbles. Yeah, those are big cobbles. If you want to remember this, which I wouldn't, fine gravel is anything bigger than 2 millimeters. Coarse silt, so between that and sand, between gravel and silt is sand, and that starts at 0.02, and between the top of silt and the bottom of silt, you're getting down to 0.002, which is probably what they were thinking when they created this thing. What we tend to use in this course, because this is what I asked you to, is the Folk system, which is ever so slightly different. And essentially, when you are describing a petrofabric and you're saying this is fine sand, you need to, at the beginning, say if you're publishing it, say, when I say fine sand, I'm using Folk 1980. That's what I'm using. And there's not a lot of it. I'll quickly go back. So fine sand is 0.125 to 0.25. So fine sand here is 2 to 6.3. No, that's fine gravel. I forgot where it was now. Where was it? Fine, okay. Medium sand, 0.25. Medium sand, 0.2, 0.63. So it's slightly different, but not very different. So medium sand is medium sand. But you should say who exactly it is you're using for your terminology. So rudites, from the Latin rudus, meaning broken up stone. And so this includes conglomerate, which is a rock made of big cobbles like this. You can see it's all endured together. It's all stuck together. Breccia, which is made up of angular rocks in a matrix. It's a rock made up of angular fragments. Grit or grit stone is like a sandstone, only very, very coarse. And gravel. Gravel is not indurated. It hasn't become a rock. It's just lumps of rock sitting on the surface, like this. So these are gravel beds, and you can see gravel is deposited at very high regime depositional rates. This is like a mountain stream, and it's moving logs as big as this, and rocks as big as that. And also, you know, if we're getting into the archaeology of stuff, this might be where you'll find small flecks of gold, because gold needs a lot of regime to get it downstream, a lot of energy in the stream regime. Here's a breccia. This is an important breccia from Egypt. This is Tawaret. You see he's brecciated. So into the sandstones. One thing to remember about sandstones is they aren't always quartz. I don't actually know what this is, but you can see it's not quartz. This looks like quartz, but this clearly isn't. And of course we get sand in pottery. This all looks like it's quite natural, subangular to subrounded, and so this is probably a natural deposit in this clay deposit. It's not angular so that it's been crushed. And so this is where we would want to look at these sand grains and say, are they angular, or are they rounded, or well-rounded, or sub-rounded, or angular, or something? And so, of course, don't use this, use the ones I use in the manual. But, so you'll want to describe your sand, and also the sortedness. Is it badly sorted, or is it moderately sorted, or is it well sorted? And so this is how we classify the different sands by the roundedness and sortedness. There's also, what is the sand actually made of, which of course matters a great deal if you're doing petrology of pottery, but actually matters quite a big deal to geologists as well. And they have various types of sandstones based on what is in it. For instance, a lith arenite, arena of course is sand in Latin, in ancient Rome, arena. So the arena where you would play games or fight or something is actually covered with sand to soak up the blood and dirt. So the lith arenite is an arenite with liths in it, with rocks. So you can see this has got bits of rock in here as part of the sand. So this looks like a very complicated diagram, but it's actually quite simple. So you have Arenites and you have Wackes. Okay, often called grey Wackes, which is even more a fun word. Wackes contain more than 10% matrix. So that's like fine stuff that is not sand sized. So this will be clay sized and silt sized material. And you typically get these in deep oceanic environments where there's less sorting by stream regime. So an arenite must contain less than 10% matrix. So up here, 10%, 10%, that's a Wacke. And this is not. Okay, this is, yes, this is how much is matrix. Oh, these are all Wackes, okay. So Arcos, or feldspathic arenites, so that's a sandstone with a lot of feldspars in it, contain less than 50% lithic, because if they get more than 50% lithic, they are lith arenites, and less than 10% quartz. So they have a significant amount of feldspars. And here's an example of one. You see here's a microcline. Remember microcline? There's one down here too, another one here. This photograph is kind of funny. Here's some plagioclase. So there's a lot of feldspar in here. So you could call this a feldspathic or Arcos, a feldspathic arenite or an Arcos. So this is actually much simpler than all of this, so don't worry too much about all that. So there's a lot of sandstones that you can make objects of as well. As I said, there's a lot of sandstone in Egypt. This is not the usual sandstone, the Nubian sandstone, which is over most of Egypt. This is a very nice, well indurated quartzitic sandstone, which is probably from the Precambrian basement. But you can see preserved in it are bedding planes from when this was sand being deposited by either waves or by wind building up like this, and it gets leveled and starts again. This is Nubian sandstone. I particularly like this figure, or this head of this figure. This was, I've seen this in real life. This was in a British Museum show that came to Toronto. And when you first meet this chap, and it really unfortunately doesn't show up here, he glints. Sort of like a vampire in those horrible vampire books that people like. He glitters. And the reason he glitters is because he's got lots of cleavage fragments. Because Nubian sandstone is an arcosic sandstone. It's got feldspars in it. And so some of the sand grains have broken along cleavage planes. And so they shine. The light shines off of them. And so he sort of glitters. If you get the light just right, and they didn't have the light just, or they thought it would be confusing in this photograph, but if you saw him in real life in a gallery with the light shining off of him just the right way, when you move, he would sort of like glitter. Lots of little glittering going on. Sparkly guy. That's probably why he's smiling. And of course, there's lots of work being done on thin sectioning all these sandstones to try and differentiate between sources in Egypt. See? So then we come to the fine grain materials, silt-sized and clay-sized. So things can be clay-sized without being clay, which is one of the things that differentiates between the rocks, because a shale, often called an argillite, which is something made of clay, argillus being Latin for clay, is fissile, like this. It breaks along in flat sheets. This is because of the high clay content. Phyllosilicates, you might even say. Mudstones or lutites are not fissile, and so because it doesn't have all the clay minerals in it, but it has clay-sized particles, and so that's the difference between them. This may be some sort of thing like that. This is what they often call a grey wacky, but he does look kind of shaly. But we'll see. So here, now we look at some of these sedimentary rocks in thin section. This is the edge of an inclusion in a piece of pottery. See, here's the other edge. And so this is actually a fragment of sandstone in the pottery. And here it is in plain polarized light. No, this is cross-polarized light. So it has some sort of ferruginous matrix here. And so quite often, one thing you'll find is if you have fragments of sandstone, you might find that there are sand grains throughout the pottery matrix of exactly the same size and saltedness and mineralogy as the sand grains in the sandstone. Because quite often what happens is this has been broken down to make tempering for the pottery. This is much more finely grained, and this is a silt. So this is a fine-grained silty deposit from the Zagros Mountains. This is a fragment of shale. So this is a better one. See here again, we're in the Zagros Mountains, which once was a deep oceanic basin, very fine deposits, and so this has all been turned into shale, lots of clay minerals, the occasional bit of silty quartz, and that's what shale looks like. Here's more shale. See again from the Zagros Mountains. So then we come to the chemical biogenic precipitates, and of course things die, make rocks. So the precipitates or evaporites, oh dear, all come in one go. Chemical precipitates, formed by precipitation of dissolved minerals from water during evaporation. So that includes travertine, which is made of calcite, gypsum, made of calcium sulfate, and halite, which is sodium chloride. So all of these things precipitate from seawater. Here's travertine, nice picture, and this is travertine. So-called Egyptian alabaster is made of calcite. And this is a mine for it. Interesting. And of course the alabaster from Mesopotamia is gypsum, which is also a precipitate. Possibly more important from certain viewpoints is the siliceous precipitates from organisms with siliceous skeletons. And this makes chert and flint and things like that. And of course, this is cryptocrystalline or microcrystalline quartz, and you can do fun things like make tools with it. And so it's quite important, if you like, tools made of stone. And of course, some of those siliceous skeleton organisms are radiolaria, and so they will create radiolarian chert. And so this is one of many textures of, and here's more radiolarian chert actually in pottery, many textures of of chert. Here's a radiolarian chert, and here's a not a radiolarian chert. Something else going on here. And so this can be used to differentiate between different sources of flint by thin sectioning it and looking at the distinctions between them. This, for instance, is a very different chert used as the material for a stone paste from Kashan in Iran. So the Carbonate Rocks, limestone and Dolostone, calcite and Dolomite. So we talked a bit about this. This is tremendous fun. This is mostly to show you two words, sparite and micrite, which you've been introduced to before, which in this case shows you what is the matrix with other stuff. It could be ooites or shells, bio stuff, pellets, pell sparite, pell micrite. But this is mostly to show you, aren't there a lot of different fabrics of limestone? So if you are looking at your pottery, say one day, and you have a pile of pottery from some part of the world, you're trying to distinguish between them, and you find, oh my golly gosh, it's filled with limestone. So you need to start looking at textures of limestone, because you will find they're not all the same. And so you will be able to possibly distinguish between different sources of pottery based on different appearances of the carbonate. Honest. So, like that. This, for instance, is an oolite. Oolites are awesomely cool things. So this happens when you have this ooze of calcium carbonate at the bottom of a shallow sea. So you just imagine this shallow sea, nice warm shallow sea, and there's like this like current going backwards and forwards in this shallow sea, and at the bottom of the shallow sea is this ooze of carbonate, and then for some reason it starts to form little balls, and the little balls roll backwards and forwards through the ooze and eventually turn into bigger balls. And so you can see that all of these balls start off as teeny tiny balls and become bigger and bigger, bigger and bigger balls with accretions of calcium carbonate. And these are called oolites. You can get oolitic phosphatoid as well. Tremendous fun. Dolomite, as I showed you, or dolostone, is a chemical replacement of calcium carbonate through the action of magnesium-rich fluids. And so here you can see this is calcite, which was stained pink, and this is dolomite, which grew in it. And this has become completely dolomitized, but you can still see these relics of the crystals which grew, completely replacing any texture that was there before. So here is micrite, and here's sparite, calcite. And so this, in this case, it was broken up and added to the pottery to make cooking book. Oh, too quick. This is a Belizean fabric from the north of Belize, where it's predominantly limestone. Here's another big chunk of limestone with nice little crystals. So this is a limestone that was probably kind of like a sandstone, only the sand was made of lime, which it probably is in Florida, for instance. If you're standing on a beach in Florida, in southern Florida, the Keys or something, the sand, the Bahamas almost certainly will be a sand made of fragments of shell. This is a carbonate, but it has quartz in it. So this is actually a sandstone with a lot of carbonate as a cement. And here we have something weird, you get some fossiliferous thing going on in this chunk of limestone. And this actually looks like coral, which is also fun. And this, I don't know what's going on here. This looks very organic. This is a lump of carbonate, and you can see it's being replaced. This is calcite being replaced by Dolostone, Dolomite. Dolostone, yes. No, Dolomite is the mineral, yes. And so, in this case, we can say, yes, the carbonate in this is calcite being replaced by Dolomite. So, and then we have the phosphatoids made of dead animals, very low birefringence, very important to remember that. So this is a piece of pottery, and the phosphatoids of course come from bones, as a fragment of bone, but also when these are deposited at the bottom of the sea, they all become oozy, and the phosphate comes out of the bone, the bones decay, and it becomes all disgusting. It's really quite disgusting, really. And becomes this ooze. And this still looks kind of oozy, but it's a rock now, and this is a phosphatoid. And so you can see in cross-polarized light, it just looks like this strange, quite disgusting organic material. But in cross-polarized light, it has very low birefringence, almost isotropic, but not quite. And so you can see that that's a phosphatoid. And so this is a very typical fabric texture of a phosphatoid with this ooziness going on. Oh, and as I said, also ooids. These look like ooids of phosphate, again, in a piece of pottery. They've probably been weathered out of their host rock and become aplastics in the clay. So finally, metamorphic rocks. So metamorphic rocks are either gone down very far and got squished a lot, or they got cooked, or even more likely, a bit of both. And so you can see you can get magma coming up and cooking it, and you can have it going way down here somewhere, or just being pushed down by the weight of the rock above it, and that'll create a great deal of pressure, but also it's kind of hot down there anyway, so you get both. And this comes up with this awesome diagram, which is probably giving you a bit of a headache. It's very colorful, but you can see this is the basis of metamorphism: pressure versus temperature. Okay, and you're going to want to know the difference between the regional, which is up here, regional metamorphism, and thermal, which is down here. So you get a lot of amphibolites with amphiboles in it, and green schists and things like this down here, and you'll get a lot of things called eclogites, which look a lot like granite, only their mineralogy is completely out. So metamorphic grade is very important. So you have low grade, intermediate, and high grade. Sometimes you might call them green schist, amphibolite, and granulite. Granulite looks a lot graniticy. And so sometimes they might call this a slate, a phyllite, a schist, a gneiss, or a melt. If it melts, of course, it stops being metamorphic entirely. These are common minerals for each of those. Chlorite is a very useful rock. Again, you can make things out of it, and we get it in pottery. Olivine. Again, you can make things out of olivine, low-grade metamorphic rock. You can see here how it's still got some of the structure of the olivine, but it's being replaced by serpentine. See, olivine becomes serpentine. What's quite important is it keeps the magnesium and the silica and adds water, but loses the iron. And so you'll have lots of iron in these deposits with the serpentine. You have lots of all sorts of things. You'll have copper as well. And we get serpentine in pottery. So I showed you these before. So serpentine is quite important. Talc. This is talc, which is also magnesium silicate. Slightly higher metamorphism, you see. Serpentine was down here. And you can make things out of this as well, and also you find it in pottery. Biotite is typical of a more higher low-grade metamorphism, and you get a lot of biotite schist, well, it's schist is here, and that sort of thing. This is a garnet schist. You get a lot of biotite in here, and mica and that sort of thing. Garnet's very typical of intermediate grade. Marble tends to be an intermediate grade metamorphic rock, where all of that limestone has been melted down. So marble is very important archaeologically. People get very keen on studying marble, and so of course they do thin sections of it to distinguish between all the different sources of marble around the Mediterranean, of which there are many. And of course we have lapis lazuli, very blue, intermediate. It's very closely related to marble. The white is in fact calcite. So it's the same sort of metamorphic thing. And that's the end of the lecture. So that should have given you a vague idea about rocks in thin section of an archaeological relevance. Rocks are things you can make things out of, and you might want to distinguish between them. It could be a mano matate in Central America, or a marble statue in Greece, but by thin sectioning you can distinguish between their production centers or the origin of the material. And of course understanding rocks is very important if you're looking at pottery thin sections. And so you should understand rocks, but really they're quite simple. You can identify the minerals, you can identify the rocks. Thank you.